Hello dear viewers, you are most welcome to this presentation of our chemistry item 003, and if you are on this channel, just hit the subscription button and like the video. On this channel we present chemistry content in terms of question papers, items and their responses like this one, and notes. So in this video we are going to go through this item 003 and have its solution, rather the expected responses to it. Just watch up to the end, and in case of any inquiries you can just drop a message in the comment section. So now let us dive into this video and have the response to it. So I always tell my students that whenever you are to answer these scenario based questions, always begin by first reading the tasks, so that it can give you a clue of what is required in the scenario. So that means you are going to begin by reading the questions under this item. So we have the task, we have part A up to part D. Part A reads, calculate the molecular mass of each compound in the table above, and we've been given the RAM of the elements. Then Roman number 2, part A, we have to calculate the percentage composition of nitrogen in each fertilizer provided. That means up there we've been given fertilizers. Then part B, arrange these fertilizers with respect to percentage compositions of nitrogen, starting with the highest and ending with the least percentage fertilizer. Make conclusion on the fertilizer which is best for farming. Then part C, explain the importance of the following during nitrogen cycle. We have Roman number 1, nitrogen fixation and nitrification. Roman number 2, assimilation. Roman number 3, ammonification and nitrification. Then part D, we have to obtain the diagram to show the major stages of nitrogen. You have to draw a model of the nitrogen cycle. So having read data 6, that means we can now comprehend on it by just reading the scenario. So the scenario reads, you have been provided or given 5 fertilizers whose percentage composition of nitrogen in each compound is not known. The farm manager would like to know which fertilizer is the best. So we have the table here drawn, having the 3 columns. In the first column we have the fertilizer, the second column we have the chemical formula of the fertilizer, and then the third column we have the percentage composition of nitrogen present. So among the fertilizers we have ammonium nitrate, we have the ammonium sulfate, potassium nitrate, calcium ammonium nitrate, which we call the CAN, and then lastly urea, each with its corresponding chemical formula. Let us now officially go to the responses in here, and we have to begin with our first part and serving Roman number 1, where it requires us to calculate molecular mass of each compound in the table, of each fertilizer, rather compound in the table. So in the table we have the first fertilizer, which is ammonium nitrate. So we are now determining the molecular mass, let me call it masses, of the fertilizers given in the table. So the first fertilizer is the ammonium nitrate fertilizer, which has a formula of this. So basing on this formula, we are now to calculate the molecular mass. Simply in here, we are going to be using the RAM of each and every element present in the compound or in the fertilizer, and then multiply it by the number of atoms. So in here I can see that we have 2 nitrogen atoms, so we can have 2, then multiplied by the RAM of nitrogen, which is 14, plus I can see we have 4 atoms of hydrogen, multiplied by the RAM of hydrogen, which is 1, then plus oxygen, we have 3 atoms, the RAM of oxygen is simply 16. So as I simplify here, 2 multiplied by 14, I'm getting 28, plus the 4 plus the 48. So the whole of this one is giving me 80 when I sum. So that means this is our molecular mass for ammonium nitrate. We can now go to the next fertilizer, which is ammonium sulfate. So ammonium sulfate has a formula of this. We have a 2 here, then the sulfate. So this is the formula. Then we have to calculate its mass. In here we can see that we have 2 atoms of nitrogen, so 2 multiplied by 14, then plus So we have 8 atoms of hydrogen, these 2 multiplied by 4. So we have 8 of them, but multiplied by the ram of hydrogen, plus we have 1 atom of sulfur, multiplied by the ram of sulfur, which is 32, plus we have 4 atoms of oxygen, multiplied by the ram of oxygen, which is 16. As we simplify, we are getting this is 28 plus 8 plus 32 plus 64. So when I sum all these ones together, I'm getting 132 grams. So this becomes the molecular mass of the fertilizer ammonium sulfate. Then let us go to the next one, which is potassium nitrate fertilizer. So we on potassium nitrate fertilizer. It has a formula of this. We have potassium and then the nitrate. We have 1 atom of potassium multiplied by the ram of potassium, which is 39, plus we have 1 atom of nitrogen multiplied by the ram of nitrogen, which is 14, plus there are 3 atoms of oxygen multiplied by the ram of oxygen, which is 16. So as I simplify, this is 39 plus 14 plus 48. So when I sum all this one together, I'm getting 101 grams. So this one becomes the molecular mass of our potassium nitrate fertilizer. We can now go to calcium ammonium nitrate, which is the same as, we always abbreviate it as CAN, calcium ammonium nitrate, and it has a formula of this. We have the calcium and then the ammonium nitrate, but we have a 2 here. So this is the formula of that compound of fertilizer. So in here we are going to calculate its molecular mass. We can see that we have 1 atom of calcium multiplied by the ram of calcium, which is 40, plus in here we can see inside the brackets we have 2 atoms of nitrogen, but multiplied by 2 to give us 4 atoms of nitrogen total. So there are 4 atoms of nitrogen multiplied by the ram of nitrogen, which is 14, plus here inside the brackets we have 4 atoms of hydrogen multiplied by 2 becoming 8, then multiplied by the ram of hydrogen, which is 1, plus inside the brackets we have 3 atoms of oxygen but multiplied by these 2 to give us 6 atoms multiplied by the ram of oxygen, which is 16. So this is equal to 1 simplified equals to 40, plus this one is becoming 56 plus 8 plus 96. So when I sum all these ones together, I'm getting my value to be 200 grams. So this becomes the molecular mass of our calcium ammonium nitrate fertilizer. Then the fertilizer we are left with is the urea. So we got urea and it has a formula of this. So its molecular mass is going to be, now there are 2 atoms of nitrogen multiplied by the ram of nitrogen, plus there are 4 atoms of hydrogen multiplied by the ram of hydrogen, which is 1, plus 1 atom of carbon multiplied by 12, which is the ram of carbon, plus 1 atom of oxygen multiplied by the ram of oxygen, which is 16. So once I simplify, this is giving me 28 plus 4 plus 12 plus 16. So altogether when added, I'm getting 60 grams. So therefore I've come up with the molecular mass or masses of these compounds or fertilizers. Then you can now proceed to Roman numeral 2 of our part A, which requires us to calculate the percentage composition of nitrogen in each fertilizer provided. Our part A Roman numeral 2, we are to calculate the percentage composition or compositions of nitrogen in the fertilizers. So let us begin with the first one, which is the ammonium nitrate. So we can say that for the ammonium nitrate fertilizer, we are going to have, so there are 2 atoms of nitrogen, so we have 2 multiplied by the ram of nitrogen, which is 14, divided by the molecular mass. So in here the formula we are using is that to get the percentage composition, we are getting the mass of the element present divided by the molecular mass, then multiplied by the 100%. So in here, the molecular mass of ammonium nitrate fertilizer, we got it was 80, then multiplied by the 100%. As I computed this, I'm getting the 28 divided by the 80 multiplied by 100%. This is giving me 35%. We can now go to the next one, which is for ammonium sulfate fertilizer of this formula. So this is equal to Still we have 2 atoms of nitrogen multiplied by now the gram of nitrogen divided by the molecular mass of ammonium sulfate, which was 132, then multiplied by the 100%. So this is the same as having 28 divided by the 132 multiplied by 100%. As I press the calculator, I'm getting 21.2%, and it is correct to 1 dp. I'm getting a recurring decimal, which is 21.212121. I've just rounded off to 1 dp. So this is now the percentage composition of nitrogen in ammonium sulfate fertilizer. We can now move to the next fertilizer, which is for the potassium nitrate. So this is equal to, you can see we have 1 atom of nitrogen in there divided by the molecular mass of potassium nitrate, which is the 101, then multiplied by 100%. Once simplified, this is the 14 divided by the 101 multiplied by 100%. So as I press the calculator, it is giving me 13.9%. I've just rounded off to 1 dp. Then you can proceed to the next fertilizer, which is the CAN. The CAN, I said, same as the calcium ammonium nitrate, and its formula is the calcium, then the ammonium nitrate, but we have a 2 there. So now this is gonna be equal to, we can see we have inside the brackets, we have 2 atoms of nitrogen, but multiplied by 2 to make them 4. So we have 4 atoms of nitrogen multiplied by the gram of nitrogen divided by the molecular mass of calcium ammonium nitrate, which is 200 multiplied by 100%. So this is the same as having 56 divided by the 200 multiplied by 100%. As I press the calculator, I'm getting the percentage composition of nitrogen to be 28%. Then the last one is for urea, having the formula this. So this is equal to, so we have 2 atoms divided by the molecular mass of urea, which was 60 multiplied by 100%. So this is the same as having the 28 divided by 60 multiplied by 100%. As I press the calculator, I'm getting the value to be 46.7%. It's correct to 1 dp. So now these are the percentage compositions of these fertilizers. That is for part A, Roman numeral 2. Then part B, we have to arrange these fertilizers with respect to the percentage composition of nitrogen, starting with highest and ending with the least percentage fertilizer. Make conclusion on the fertilizers, which is the best for farming. To arrange these fertilizers basing on this percentage composition, basing on this, and I said we should start with the one having the highest percentage composition. So there are 5 fertilizers. So this one is having 35. This one, ammonium sulfate, is having 21.2%. Potassium nitrate is having 13.9%. Calcium ammonium nitrate is having 28%. Whereas urea is having 46.7%. So urea is having the highest. That means if I'm to arrange, I'm going to begin by writing the urea, having this formula, can use greater than, followed by the ammonium nitrate, then followed by the calcium ammonium nitrate, followed by the ammonium sulfate fertilizer, then lastly the potassium nitrate fertilizer. So we have so far arranged. Then they say they can decide to make a conclusion the best fertilizers for farming. I can say that therefore the best fertilizer for farming is urea. The formula is this. We can now give a reason. This is because urea has the highest percentage composition of nitrogen, which is essential to the plants to make a chlorophyll, organic compounds like the plant's DNA and the proteins. So in other words, the nitrogen helps the plants to do well. That's why we have to choose the one having the highest percentage of nitrogen in it. We can now proceed to our next part, which is part C of our question. They say explain the importance of the following during nitrogen cycle. We have Roman number 1, nitrogen fixation and nitrification. Part C, Roman numeral 1. We are to explain the importance of nitrogen fixation and nitrification. We know very well that in the nitrogen cycle, nitrification, first of all, it is important in conversion of the atmospheric nitrogen into ammonia, and it is added to the soil or into the soil. So we can now therefore say that nitrogen fixation is important in conversion of the atmospheric nitrogen into ammonia or ammonium ions by adding it into the soil. So remember, this nitrogen fixation is facilitated by processes like lightening and also by some bacteria, for example, rhizobium bacteria, which is found commonly in leguminous plants, specifically in the root nodules. So these bacteria, they help or they aid in addition of nitrogen into the soil in the form of ammonia by absorbing it from the atmosphere. Then for the case of nitrification, converts ammonia or the ammonium ions into nitrates, and nitrates that can be absorbed by the plants. And this nitrification process is facilitated by bacteria like Nitrosomonas and Nitrobacter bacteria. So the Nitrosomonas facilitates the conversion of ammonia or ammonium ions to nitrates, and then the Nitrobacter bacteria converts the nitrates to nitrates. We can now move to Roman numeral 2 of our part C, which requires us to explain the importance of assimilation. Assimilation allows the plants to absorb inorganic compounds from the soil in the form of nitrates or nitrates, which they use to make important molecules in them, like DNA, proteins, chlorophyll, etc. So this one allows the plants to absorb, or the plants absorb nitrates or the nitrates from the soil and use them to do well. Then you can go to Roman numeral 3 of our part C. We have to explain the importance of ammonification and nitrification. This is Roman numeral 3 of our part C. Ammonification allows the addition of ammonia back to soil. This is through excretion of the animals and plants, and also when they die and decompose. So it allows nitrogen to be added to the soil from the plants and animals. As they die and decompose, the inorganic compounds containing nitrogen that are in form of ammonia are added into the soil, which are later converted to nitrates and nitrates by nitrification. Then, seeing this very Roman numeral, we need to explain the importance of the nitrification. So this one allows the conversion of nitrates and nitrates back into the atmosphere in the form of nitrogen gas. So it is this process that involves the conversion of the nitrates and the nitrates containing or contained in the soil to evaporate into the atmosphere and go back into the atmosphere. Then we have our part D, which is the last one. Obtain the diagram showing the major stages of nitrogen cycle. So we have to draw a model of nitrogen cycle. Model of nitrogen cycle. So I can have this, and it's noting the ground. So this is the ground or the floor. So this side we have the atmosphere. Then this way we have the ground, or we can call it the land. So we have the nitrogen gas in the atmosphere. It is added to the soil this way, and this process is the nitrogen fixation, and is added to the soil as ammonia or ammonium ions. So that is into the soil. Then while in the soil, the ammonium ions or ammonia are going to be converted to nitrates. Can say nitrates or nitrates, and the process in here is the nitrification by some bacteria, like as I've told you earlier on. Then the plants, if you have the plants in here, they have their roots. These plants are going to absorb these nitrates, and the process here is called the assimilation process. So they use them, and now also these plants, when they die or excrete, they release ammonia back into the soil, and this process is called the ammonification. Whereas nitrates, when they are into the soil, they can be converted back into the atmospheric nitrogen, a process denitrification. Also, when the animals feed on these plants, and these animals can excrete or die and decay, then they form back the ammonia through the process of ammonification. So we shall have it saturating in the earth, water, land continuously like this. So thanks for watching. If this video has been of value to you, kindly subscribe to the channel for more videos on chemistry. See you again next time. Goodbye.